Okay, so yes, so that will take us to statistical distributions, right? So now we kind of like have all this probability knowledge all set and ready. We can actually use this to create new things. So a couple things I want to mention, we only have about 15-ish more minutes, but so just know that we won't go through this whole part of statistical distributions. We'll save this for next time, and this will lead us into also when we start looking at linear regression. So first thing I want to note is that when we have a randomness, which we'll use in our distributions, basically our randomness is going to give us a little extra like noise essentially. But note that when you do a random number on a computer, it's the same random number in a lot of ways, which is kind of weird. But basically, because computers cannot actually be random, they have to, kind of by definition, the function has to produce the same output no matter what. So the problem with that is like, well, if you know the same output every time, how do you make something random? How do you have the computer generate something random? And there's a bunch of ways you could do this. One actual real solution is trying to use the real world and try to use the real world data to try to get a randomness number. If you remember back, maybe if you took statistics back in like, high school or even like, college or university, right? You might have seen like random number tables. I don't know if that even sounds familiar to anyone. Okay, see some nods. So that one is like, oh, you have the same random numbers. That's essentially your function, but you're, depending on how you do it, you might choose, if you have this table, you might choose different spots on the table to start with, or you might, for example, count by different numbers or something like that to make sure you get a randomness of the random numbers. And that's essentially what the computer is doing. It basically creates a really complicated function, which we won't go into, but basically it creates a complicated function that seems random, which we call pseudo-random. So it's creating pseudo-random, meaning like fake random, but random enough where it doesn't really make sense. So I kind of gave it a couple comics. Of course, XKCD, if you guys don't know, xkcd.com, amazing website. Basically, it's always going to be relevant to you for all of these math and computer sciencey stuff. So this is from them. You can see right there, they're creating a function, not really any programming language you guys know, but they're making a function, get random number, return 4. So, I mean, technically 4 is a random number. It's just giving you the same random number every time. Same thing for this comic. This is a pretty famous one too, where a person is giving 9 the whole time and it's still random. So like, again, this is what we kind of want to avoid. We don't want to have it literally give the same random numbers. So we do something called a seed. And that's what this np.random seed here is. And basically it creates this np.random seed. I just give it a number essentially and say, all right, start off with this seed, this start off point, and this will reproduce the same random numbers every single time. So I just ran this right now. So I ran this with random seed. And if I run this now, this will grab a list of random numbers or integers between 1 and 10, 5 different times. So you can see they'll give you a list of 5 random numbers. And if I run it again, this other part right here, you'll see 5 new random numbers, right? And so you can see 49991, 69923 and 2. All right, so you're like, okay, cool. Like that's awesome, but how do I know those are actually, like those are technically random? And if I run this again, just to kind of, I don't want to erase it, but if I run this again, you can see new random numbers. I can keep generating new random numbers over and over. Now, if at any point I'm like, well, let me restart this now. So I'm gonna go ahead and restart the kernel just to make sure I flesh things out. And I go ahead and run this part now. I can reseed it with the same exact number, 27, and I'll get the same random number. So you'll see when I run this, you'll see 49991. If I run this, 49991. If I run this now, you'll see 69232. Same thing. If I run a new part now, you'll see some new random numbers that we saw before, but we don't remember exactly what they were. If I put in a new set of numbers, if I put the number 2 and did a seed, let's not restart it. Sorry, restart. And I do this now, we'll get a brand new set of random numbers. And you can see they're not the ones that we matched up before. Okay.
So
again,
can I ask a quick question? So it doesn't really matter which number you put inside, right?
In the seed, no. No. The reason, yeah.
Okay.
Sorry, go ahead.
Okay, no, that's it. Yeah, I just want to confirm that because I searched, couldn't find anywhere saying.
Oh no, it literally doesn't matter. Like, in fact, you don't actually need this random.seed. If you don't do this, I don't know what NumPy does specifically, but it basically tries to seed it itself. Sometimes it's the time, sometimes it's like how you move the mouse, depending on the program. But for our data science and a lot of machine learning stuff, we want to have it random, but we want to be consistently random so we can reproduce the same results. So this is why sometimes you'll see random seed. For example, you usually see like 42 because the meaning of life, right? I don't know if you guys know that reference. Douglas Adams, but that you'll see this very common, like 42. You'll see people put in their favorite numbers. You'll see people just put in 7. You'll see people put like 1 because, like, I don't know, they have no emotion or creativity. I don't know. But anyway, you could put whatever you want in there, right? So the whole point is basically you start off with seed, so you're always the same consistent random number. Okay. So I want to show that because that is a subtle point that you've probably seen it already and haven't really thought much about it. But whenever you see that seed, you're just creating a new starting point for your random numbers. Okay, cool. So I'm going to move on to distributions, which is really the real meat, and we'll only talk about this for the next like less than 10 minutes. So a distribution, just know, it's basically a way for us to visualize some of the stuff that we see. And so one thing I will iterate, I don't know if I've already said this before, is that the biggest part as a data scientist you can bring to being a data scientist is the fact that you're human, and the fact that you have like first of all, you can reason things. You can actually think about like, what's the context of this stuff, but also one kind of superpower that we kind of don't really think about is that humans are generally very visual and understand things visually very well. You might not realize how well that is, but you can notice patterns before that might be difficult to express immediately. And that's actually a big part of like machine learning, is trying to figure out how do you express image patterns and find these things. And so this is why like I kind of emphasize this part, is that you should always, like, if you can, make a visual for yourself at the very least. Now, that doesn't mean that you have a superpower in the sense that you don't have to use any hard-coded numbers. I don't mean that. I mean that you have the ability to look at information and find patterns. In fact, this might actually be too good. Sometimes we find patterns that don't actually exist. This is why randomness actually, when we try to make things that are random, that look random, we actually structure in a certain way to make sure it looks random versus what we think is not random. But just know that we can find these patterns, and that's why we actually do these visualizations, because we can find these patterns and say, okay, that looks interesting. Let me investigate further with some hard-coded information. So I have this distribution here. In this case, we're actually using a normal distribution, which we'll talk about what it's going to be next time. But just know that this is basically just using NumPy's random package using a normal distribution. So it's going to create some random numbers essentially, right? And I'll just put 27 here just to make it consistent. I want to make sure for future stuff that we do, I'm not going to run this part because I didn't have that before. Okay, just so it's consistent for next time when you see it, is that we're going to create this normal distribution. Okay, which I haven't really talked about what this is. Basically, it's picking out random numbers in a certain way, and it's going to use these numbers, mu, sigma. Again, we haven't really talked about this, but just know this is like going to be some parameters that are specific to the normal distribution. Essentially, you can think of it like the average versus the standard deviation, and then just saying we're going to pick 5,000 numbers. Okay, so that's what this is. So I'll run this part. So now I have a distribution, dist, that has all these random numbers. Okay, and I have this file here. I'm just reading into a data frame. You guys have seen this before. And I'm going to take this distribution, and basically I'm saying, okay, this is going, oh, well, that was dumb. That's why I count this out. We're not going to use that part. My bad. This is past Victor messing me up again. But we're going to read this data frame over here. And this case is going to be a bunch of information, and we're going to get the housing median age, and we're going to do basically take the average of this to get the mu, and then the sigma part right here. So I'm going to show you what this looks like. So this is like a real, of course, because I didn't run that, because I restarted the kernel. So now if I run it, okay, now it's basically just reading this information. And so this mu and this sigma, these are predefined. These are defined by the data that's in here. So if I were to just kind of put in like df.head, just to see that, you can see there's all this information here. So in this case, I got just the housing median age. So I got this part right here, all that column. And basically say, what's the average of this? What's the standard deviation? In case STDV or STD, right? So that's my standard deviation. And now I can actually plot this out. So when I plot this out, you can see this wonderful distribution. And I'm showing you this, like, why we use distributions. The reason why we use distributions is so we can see visually what's going on. We can see how the distribution of this housing median age, whatever that's supposed to mean. And in this case, I put a few things. For example, I saw the average right here. Okay, and I also have these green lines, which are basically one standard deviation away. So if you remember, we talked about standard deviations. This basically is one standard deviation from each part. And then this right here, I didn't really talk about this, but this basically, we'll talk about what this looks like in a second, but this is basically a density approximation. So this is basically the function trying to figure out, like you can see it's continuous, or not continuous, it's discrete, where we have like, oh, there's so many that are in this age, and so many that are this age, so many that are this age, because they're all integers right here. And so basically what happened is that it's trying to figure out what would be a smooth looking function. What would that look like? And it creates this part. So this kind of gives us a lot of information. You can see there's some peaks. You can see where the average is. You can see where it tapers off. You can see that this blue line right here is basically, what's it called? Like, it doesn't quite estimate everything exactly because there's nothing over here, but it says that off of this part, it's like, oh, it should taper off, but there's nothing here. So just know these are the things that we're going to talk about in the future. So these are a bunch of things going on. And
Victor,
I wanted
to ask,
yeah,
you were saying that it's showing the average. It's actually like the median, right? Because if the distribution was not normal, then the average and median would be the same, right?
Yeah, it turns out this red right here is the average, just by the way I defined it, because I defined it by this right here. That's just the way I graphed it. I could have done like the median, like let's just do median just to show it off, right? And now these should all be the same, except this will be the median now, and you'll see now the median, oh, turns out to be about the same.
Yeah.
So,
okay,
yeah.
cool, thanks.
Yeah, no problem. So again, but a good point is that it just turns out that this tends to be relatively normal. So that's kind of why it's ended up being right there. Okay. Now, this is why I put this out of order. That's why it's messing me up, is that I can also define my own randomized distribution, in this case, a normal distribution, what Tara just said, basically about saying, oh, we can have a normal distribution. And this way we define what 14 is going to be our average, 2.8 is going to be a standard deviation, and we're going to have 5,000 points. So I'm going to sample out those points. So I believe I ran that. So I run this now. I can now run this part. Do I have? No, I have everything there. So now I can run this and actually show you what that normal distribution looks like. And you can see basically it randomly picked out, when I ran that distribution top right here, it basically created a bunch of numbers and essentially what this column represents, and plot this out. And we actually have this blue line here, which tries to estimate it, which is actually really close, but you can see it's still not perfect because there's some peaking. And you can see here's the median right here, down the middle. Okay, I'm not median, the mean right here. And we have the standard deviations on the side, one standard deviation each. Okay, so again, and you can see if you look carefully, that's about 14. And you can see that's about where it's peaked up. So these are different distributions. This is more of a generated distribution, which is more normal, it turns out, versus this housing data right here, which was not, it's not technically normal, but you can see that what Tara was saying is like, oh, it turns out the median and the mean actually are pretty close. So it's relatively close to being a normal distribution. But these are things that we're going to talk about then to explore. So kind of giving ahead is, and if you guys already looked at section 9, this is what you will talk about for the future, is the probability mass function, the cumulative distribution function, probability density function. Basically these guys right here, this PMF, okay, and this PDF, we'll usually take this PMF and convert it into a PDF, where it's a continuous probability function. And we'll talk about this again. And then we'll talk about normal distribution, like down here, and then deviations from this normal distribution. Okay. So again, we'll talk about this next time, so don't freak out. But if you want to look ahead, if you're already on section 9 and you want to read some of this stuff right now that I have in here, it's on the GitHub right now. And then we'll go over it for next class or next study group. I call it class, but it's a study group on Thursday. Cool. So any questions about stuff I showed up here?